So let's put it up. Hahn-Banach Theorem. Hahn-Banach Theorem. Right. Says that given V a real vector space, and given some real value function p, given some real value function p that is p is sublinear. In other words, p of alpha v equals alpha pv for all alpha greater than 0, right? And 2, p of v1 plus v2 is less than or equal to p of v1 plus p of v2, right? For all v1, v2, and p. Right? You see that, for example, a norm on your vector space is a sublinear function. So p is something like norm. Given the vector space, so let V naught be a subspace of V. Given any linear functional, L naught on V naught, such that L naught V is bounded by P of V for all V is V naught. There exists an extension, there exists a linear functional L on V, such that one preserves this relation on the whole subspace, and 2, L restricted to V naught is L naught, right? L is an extension. L is an extension of the linear functional that we started off. Okay. So the proof is basically as Anna says. Well, you say we're going to extend it. We're going to try to extend it one dimension at a time. We'll show that if we have a subspace, we can extend it up one dimension. We can extend it in such a case, we can always extend it up one dimension more. Okay. So right, let V1 be in V but not in V naught. So choose somebody who is not in V naught, and let capital V1 be the span of V naught and V1. So then we just create the extension L1, the extension of L naught to V1, sort of in the obvious way. You say, well, we create L1 by observing that such a guy would have to, L1 must satisfy that L1 of alpha V1 plus W, where W is in V naught, and A is a real number. We're forced that this has to be alpha L V1, right? L naught V1, no, L1 V1 plus L naught W. V1 is, of course, the guy who is outside, right? And W, alpha is in R, and W is in V naught, right? Because it's a linear functional, right? Being a linear functional means that this relation has to hold. So that forces our definition of L1. It says in order to extend to the new space, what we need to do is to choose a value for L1 V1, right? And once we've done that, then we have a linear function that extends to the new space. Okay. So creating a linear functional that extends L0 to V1 is easy. Okay, right? The only subtlety is how do we ensure, right? So let's satisfy this. Right? In other words, extending L0 to V1 is just a matter of choosing a value for L1 V1. Right? Once you've chosen that value, then you've got a linear functional that extends L0 to V1. Okay, so the only subtlety is so the only subtlety at this point is what choice, is it possible to choose L1 V1 so that L1 alpha V1 plus B is dominated by P of alpha V1 plus B. Right? Because that's what we want. Right? We want the extension to satisfy the relation with the sublinear function. Right? So that's the only subtlety. And it turns out, and maybe we'll get into this, it turns out that it suffices to choose any value L1 V1 such that L1 V1 lies between negative P negative V1 plus W prime plus L0 W prime, so that the value lies between here and here. Okay, and I'm going to sort of skip. Understanding this is not really that complicated, but it takes a bit of time. So I'm going to put it off to the end of class. We'll do the Hahn-Banach Theorem, and then we'll do the important things, and then if there's time, I'll explain as it turns out. Right? So I'm just going to say, like, fact. It suffices to choose any values that satisfies this. Okay, and then we'll get to the fact later if necessary, if we have time. Okay. Fact. It turns out that it suffices to choose any value like this, right? So what you're hoping. So that this holds for all V and V prime, W and W prime and V naught. Okay. Okay. And so what this boils down to is saying it suffices to check if L0 of W prime plus L0 of W is bounded above by P of V1 plus W plus P of negative V1 plus W prime. Right? To check if this is true for all W and W prime in V naught. right? Because if that's true, then this is always less than or equal to this, right? This is the same. These are the same statements, of course, right? Right. So if this is true, then there's always space between the two numbers, right? I mean, they may be equal, in which case you set L1 V1 to be that number. Okay. So, right. So, are you guys following this? Right. So, you just need to check. Is it can we find space between these two things? And the answer is yes, right? Because by linearity, this is equal to this. This thing is equal to this, right? And we know that on V naught, we have the relation that P of W plus W prime dominates L naught of W plus W prime. Okay, so this happens because we know it's true for L naught, right? And then this thing is, of course, smaller than the right-hand side by the sublinearity, right? So by sublinearity, by the sublinearity of P, we know that this is, this W prime minus V1 plus P of V1 plus W, right? Like the triangle inequality, right? Just like using the triangle inequality. So, since there is space between these two numbers for each V1, we're able to choose values that make the relation hold. Right. So, right. So we're able to see that that L1 is not only a linear functional, but it also satisfies the relation with the sublinear function. Okay. So it's pretty simple. I should have just said just read it. Close your eyes for a second. Would you be happier if I just said just read it? If you'd be happy if I just said just read it, raise a finger. Okay, open your eyes, please. Nobody would be happy if I just said just read it. Okay, interesting. Okay. Okay. Yes, I'm not really sure, how impatient you are. I feel like my feeling right now is we're still in chapter 1. I'd like to go faster and faster. Close your eyes for a second. Who would raise your finger if you want to go faster? Okay. Put your fingers down, open your eyes. No, wait. Close them again. Raise a finger if you would like to go slower. Raise a finger if it's okay. Okay, fingers down. Okay. So I'd say the poll says there are a lot of people who are okay, and some of those people who are okay would also like to go faster. Okay, so that is okay. I'll speed it up a little bit. In fact, I think I'm gonna. So I'm gonna speed it up a little bit because this stuff is important, but maybe not everything, not every piece of it is important. Okay. So let's speed it up. Okay. So good. So you see how it goes, right? If you have a linear functional on a subspace and it satisfies the relation with a sublinear function, then it's possible to extend one dimension more. Right? It's not that difficult a matter to extend one dimension higher. Okay. So now, to complete the Hahn-Banach theorem, we need to use the well-ordering principle. So here's how we do it. We say, like I said earlier, regret too much keeping in chapter 1 because the set of exercises is so good and so important. The stuff that you're doing in the exercises, if I did chapter 1 in 1 week, then I would assign all those problems in 1 week because they're so good. So I think it's not a bad idea to stretch out chapter 1 to give you a chance to go through these exercises, which introduce you to a lot of ideas and inequalities that are actually used by analysts or animators, as my friends used to say, all the time. So I don't regret it, but I'm going to speed up. I am going to speed up. So, okay, so now, so we know we can extend it 1 dimension at a time, okay? How do we get all dimensions, even if they're uncountable, right? If it were a countable set, countable dimension, countably infinite dimension, then you can say, okay, just do it 1 step at a time, right? You do an induction, right? But what if it's uncountable? Well, this is why we need to use the well-ordering theorem. Okay, so given V naught, well-order, place a well-ordering on the set of vectors in V not in V naught. Okay, well-order with something that looks like this. Okay, so this is some so put a well-ordering that looks like this on, put a well-ordering this guy on the set of vectors in who are V but not in V naught. And so you consider the set of vectors for which you cannot, so let V1 denote the smallest vector. V1 denote the smallest vector for which there is not an extension of L naught, not an extension of L naught to the subspace spanned by V naught and all vectors smaller than or equal to V1. Okay. Is that clear? It's a little bit, there's a lot of language here, but you say, I'm going to look at all the vectors. I'm going to consider the collection of those. I'm going to consider the set of those for which you cannot extend L naught to the span of V naught and all vectors smaller than or equal to that vector. Okay. Is that clear? Okay. By the well-ordering principle, there's going to be a smallest guy, right? So then, if that's the smallest guy, then what that tells you is that L naught has an extension to the subspace, spanned by V naught and all vectors smaller than V naught, than V1. Right? So we throw that guy out, basically. We throw that guy out, and L naught should have an extension to the subspace that consists of everybody of V naught and everybody smaller than V1. Right? Okay. but then you extend, so let's call this subspace, I don't know, V naught prime. Okay, so L naught has the, L naught we know can extend to V naught prime, and then you just create an extension to the span of V naught prime and V1 in the way that we just did, right? We know we can always extend one dimension more, right? So let's throw that guy in now, right? Now we have, and then you create the extension to that, and now we have an extension to V naught, the span of V naught prime and V1, but that's a contradiction because we said that the V1 was one of the vectors for which there was no extension. Okay, so use the previous instruction to create an extension L1 of L naught to the span of V naught prime and V1. That gives you a contradiction. Okay? Because there shouldn't be any extension. Okay. So what does that tell you? That tells you that there is no such vector. Right? There are no vectors for which there is no extension. In other words, every vector you can get to you can get an extension to. So that's the proof of the Hahn-Banach theorem using the law working principle. Okay. Okay. So pretty simple, I think. Right? It's not really deep, but it's very important. And we'll spend the rest of the class talking about applications of the Hahn-Banach theorem. The rest of the chapter is basically applications of the Hahn-Banach theorem. Okay. Any questions? Any questions? Okay, I have a question. Where is Spencer? Does anyone know who Spencer is? No, I don't care. I actually don't care. Maybe a little bit. Okay. So now we're gonna do applications of the Hahn-Banach theorem. Okay, so this will be fun, I hope. Okay, first application is to the notion of dual linear transformations on Banach spaces. So applications on Banach. Okay, so let's start out with the definition. We have T going from V1 to V2. Okay, this is a linear transformation. I don't know if people use this abbreviation, but I do. Linear transformation between Banach spaces. Have you seen this? Has anybody seen this outside of my class? No. Okay, nobody uses this abbreviation. For some reason, when I was an undergraduate, this was always how professors wrote transformation. I don't know why. And then after I left, so this was Princeton, so not just some strange place, you know. And I assumed, what people do at Princeton should be is probably standard. But after I left Princeton, I found nobody uses this abbreviation. Maybe it's an abbreviation used by physicists. Anyway, so this means transformation. Okay. Suppose you have a linear transformation between Banach spaces. We define a dual transformation. The dual transformation T star going from V2 star back to V1 star. Okay. So think of what we're doing, right? We're starting off with a linear transformation. We're starting off with a linear transformation, I'm sorry, a linear functional on B2, right? And we would like to get, right, so we have T here, right? We have a linear transformation we have a linear functional, on B2, right? And we would like to get a linear functional, we would like to create a linear functional on B1, right? So it's sort of obvious what we're going to do, right? We have a linear functional here, we'd like to get a linear functional that goes from here to here. Oh, you're just going to use it, you're just going to take this, you're going to take this thing and map it through and then hit it with BL2, right? And that'll give you the, right? You just take the composition, right? So it's obvious, right? So you define this guy, so L2 gets mapped to T star of L2. T star of L2 is going to be a linear functional on B1, right? So it's going to go from B1 to R. Right? What does it do? It takes some function in B1, function in your Banach space, and then maps that guy to T of F1 hit with L2. So L2 gets mapped to T star of L2, which is the linear functional taking something to L2 of T of F1. Right. In other words, right, it just, right, T star of L2 is just the thing that makes this commutative. Right. It'll takes F1. Okay. Right. T star of L2 of F1 is F1 mapped through T and then mapped through L2. Okay, so that is the dual transformation, right? That's the dual transformation. You know, it gives you a linear functional on takes a linear functional on B2 and gives you a linear functional on B1. Right? We do need to show that it's a bounded linear transformation for this to be true, right? We're saying that it maps into B1 star. We need to show that it's bounded. Okay. Okay. So theorem, in fact, T star. No. That it is bounded is obvious, but sorry. We want to show that T star is a bounded linear transformation. And the norm of it is actually the same as the norm of T. So that's our goal. Right. This is maybe the most tricky thing we're going to do today, but it's not so bad, I think. As long as you keep your head straight, right? As long as you remember what everything means, then it actually is not so bad. So to get it, we're going to use a lemma that will be from the Hahn-Banach Theorem. So the lemma is like this. Given a Banach space, given B a Banach space, there exists a linear functional in B star such that when L of F naught is just the norm of F naught, L of F naught is the norm of F naught, and 2, the B star norm of L is 1. So there is a linear functional of norm 1 for which L of F naught is the norm of F naught. This is sort of nice, right? Like you can pick out this, you can make a linear functional that somehow singles out this one element. Okay, so whatever element you want, you can create this linear functional that gets it. Okay, this linear functional norm 1 that returns the norm of that guy when you feed in that guy. Okay, so the proof of this is basically use the Hahn-Banach theorem. So you make you let V naught be this space, right? Okay. You take F naught and you take all multiples of F naught. You create this one-dimensional subspace. You create this one-dimensional subspace, and you say, okay, and we're going to let L naught on this space be defined as alpha F naught, alpha times the norm of F naught. Okay, so this is clearly a linear functional on B naught. Right? So you create a linear functional on B naught. Okay, and you notice that with P of V being defined the norm of V, L naught and P satisfy the conditions of Hahn-Banach. E naught is certainly a sublinear function, and we know that it's easy to see, of course, that L naught is dominated by this guy. But it's either equal to or the negative of. So what does that give us? Right? So there exists an extension L. There exists L, linear functional extending L naught to all of V, such that, well, L of F is controlled by P, right? Such that L is controlled by P for all F and B. Okay, right. That's the conclusion of Hahn-Banach, of course. Right. Okay. And then you just observe L of negative F, that is to say negative L of F, is controlled by the norm of negative F, which is the norm of F. Right? So that tells us that the absolute value of L of F is controlled by F. Right? So that gives us that the norm of L is less than or equal to 1. And since absolute value of L of F naught equals the norm of F naught, we see the norm of L must be equal to 1. Right? It must be greater than or equal to 1, so it must be equal to 1. Right? Because the supreme, we say that the supremum is must be greater than or equal to 1. The supremum over all f naught that are non-zero must be greater than or equal to 1. And so we've got the dual space norm of L is 1, and it does this thing. So we've created, it's possible given any function to create this functional of norm 1 who takes the value of the norm on that point. Okay. Any questions? Okay. Okay. So let's get back to the theorem. Okay. Wish I had more space because I don't want to erase anything. Let me just erase this thing here. So in my notes, I have that, so the proof of the theorem. Right, we want to show that this B star actually has the same norm as T, right? So in my notes, I have that one direction is trivial. So, this direction is actually easy. So I want you to think about it I'd like you to think about it for just tell me what. So just think about it for 2 minutes, and then tell me that it is true. Or think about it for 3 or 4 minutes, and then I think this is just a matter of definition chasing. So one way doesn't involve Hahn-Banach, doesn't involve anything. It's just chasing down the definitions and noticing that it's true. Try not to use your book, but just try and look at it cold. Just say okay, so what does this mean? What does this mean? Right? That will help you help the definitions become more entrenched in your body. Okay, talk to somebody else. Talk to somebody else for a minute.
You're looking at so like linear expansion.
Okay, would somebody like to come up and explain it? Maybe get some practice as a teacher. If you're gonna do math, yes, in university setting, and I regret you have to be a teacher also. No, I'm joking. Would somebody like to come up and explain it? Or okay, maybe nobody wants to come up and explain it. But would somebody like to tell me, roughly? Let me shut the door here. So you can hear what you guys say. Would somebody like to tell me what's the idea? What do you think? What's going on here? Somebody tell me what we're trying to do? We're trying to show that the norm of T star is less than that. Well, what's the norm of T star? What do we mean when we say the norm of T star? Well, the norm of T star is what you get, right? The norm of T star is what?
Supremum over all L norm 1.
Yeah, it's the supremum over all L2 of norm 1, say, of T star of L2 as an element of B1 star. Right? Or, if you like, right, supremum over all L2, all non-zero L2, you've got this ratio. B1 star over L2, B2 star. Right? And a lot of stars here, so maybe you get confused. So let's decode. I get confused, at least. I don't know about you all, but I get confused. So let's think about what this means. This is saying the norm of this guy as a linear functional on V1, right? Right. So this thing here, right, is the supremum over F1 and B1. F1 and B1. We look at T star L2F, right? T star L2F, and that's actually just a number, right? Over the F1 norm, the norm of F1, right? Or, however you like, F1, you can make this as norm 1, and then you don't have to deal with the bottom, whatever. So is there some reason why right, and you're hoping that, right, we want to show that right, that this supremum is bounded by, right, we want to show that the supremum is bounded by the norm of T, right? It's bounded by the norm of T. Right? In other words, what we are hoping that for all L2 in V2 that are not zero, and all f1 in V1 that are not zero, that T star L2 F1 is controlled by the norm of T times the norm of L2 times the norm of F. Right? Just definition chasing. Okay. Right? But why is that true? But that's obviously true. Right? That's obviously true. That's trivial. Right? T star L2 F1 is L2 T F1. L2 T F1. Right? Right? L2 is a should be B2 star. L2 is a linear functional. Right? L2 is a linear functional, so we know that this thing is bounded above by the norm of L2. The norm of L2 times the norm of this, but T is a bounded linear T is a bounded linear transformation, right? So we get the norm of T times the norm of F. Times the norm of F. Right? T hat. Okay. So it's just the only thing you need to understand is what does the norm mean and what does T star mean. Okay. Right. So it's always sort of a hassle to decode. I mean, maybe not for intelligent young people like you guys, but for an old guy, or for me at least, for a stupid guy like me, it's always a pain to decode this stuff. So I always have to think, okay, well, what does that mean? That means, let's see what that means. That means we take the supremum of this thing. What does that mean? That means we take the supremum of this thing. We want to show that the supremum of that thing is smaller than t. What does that mean? That means this. And then figure it out. Okay. When I was an undergraduate, the professor would always say something like, when you all win Nobel Prizes, blah, 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 blah. So to set the bar high, I guess.
So,
Yes, go ahead.
L2 is linear function.
Yeah.
We don't know if it's bounded linear function.
We do because it's in B2 star. B2 star was the bounded linear function. Right. You have a Banach space, we have the dual space of bounded linear functions. Yeah, Eric.
Same question, but for T.
But for remember, T was a bounded linear transformation from B1 to B2 on the Banach spaces. It should have been I should have written a bounded linear transformation. Yeah. Otherwise, what are we talking about when we say the normal T? Right. So yeah, bounded linear transformation. Right. Otherwise, this wouldn't make any sense to talk about the normal T. Okay. So that was the easy way. Now let's go to the hard way. There's always, it's like a rule, some sort of meta rule, that there's always one easy way and there's always an easy way and a hard way. One direction is always easy. Okay, so I hope that I get this right, because I found this morning that I made some errors. But let's see if we can do it. Okay, so second part 2, we want to show that T is bigger than the norm of T is bigger than the norm of T star. Okay, so here's what we're going to do: claim that given any epsilon, T star, the norm of T star is bigger than T minus epsilon. Norm of T minus epsilon. So, okay, so let's think of what that means, right? What does this mean? In other words, we want to show that that there exists an L2 of norm 1 and an F1 in B1 of norm 1 such that T star of L2 of F1 is bounded below by the norm of T minus epsilon. Okay, so if we can do that, of course, then the norm of T is bounded below by T norm of, the norm of T star is bounded below by the norm of T minus epsilon. And it's true for all epsilon, and that'll give the set bound. Okay, so here's how we're going to do it. We're going to involve the Hahn-Banach theorem, or the lemma that came as a corollary of the Hahn-Banach theorem. Say, okay, we know there exists an F in B1 such that the norm of TF1 is bigger than T, of norm 1, such that this is bigger than T minus epsilon. Just by the definition of the norm of T. There's got to be somebody in there who is for which this is bigger than the norm of T minus epsilon. Otherwise the norm of T would not be the norm of T. Okay. So we take that guy and we let F2 so that guy, I'm sorry, it's called F1. Okay, F1. So that guy is here. Okay. So we take that guy and we let F2 be T of F1. Okay. So we map that over here, we get F2. Okay. So and that basically gives it to us. We know by the lemma there exists a linear functional L2 in B2 star. Right? This guy is in B2. We create the linear functional that attains the norm on F2. Right? There exists a linear functional such that L2 of F2 is the norm of F2. Which is the norm of T of F1, which is bounded below by the norm of T minus epsilon. Okay. But that is to say, but then T star of T star of L2 F1 equals, by definition, L2 of T of F1, right? Which L2 of T of F1, which is bigger than T minus epsilon. T of F1. Is that right? Something looks a little funny to me. Right, that would be the end. If that's right, then that's the end. But something looks a little funny. Can anyone tell me what's something is wrong here? We know that there's a linear functional L2 such that L2 obtains the norm of F2, which is the norm of F1. We know that that thing is bigger than T, so that's fine. But then T star of L2, then using that we get T of no, that's right. That's
Yeah,
right.
because we know that
Yeah,
the norm of L2 is
yeah.
1.
Right. Yeah. No, it's not because it's not because the norm of L2 is 1. Yeah, that's what confused me. Okay. Yeah. If we were using the fact that the norm of L2 is 1, we would get that this thing is bounded above by the norm of TF1, which is trouble, right? Because then we couldn't get it bounded below. But what we see is that this thing is F2. We get the norm of L2 F2. The magnitude of L2 F2. This should also be magnitude. The magnitude of L2 F2, which is bounded below by T minus epsilon, norm of T minus epsilon. Does that make sense to everybody except for me? Anybody confused? Anybody confused by that? Right, we're looking for, right, let's think about it. Right, we're looking for an L2 of norm 1 and an F1 of norm 1 such that the magnitude of this is bigger than this, right? And we think, okay, well, what is this, right? Right? Say, well, this thing here by definition is L2 T of F1, right? L2 T of F1, right? So we're looking for an F1 of norm 1 and an L2 of norm 1 so that this thing is bigger than this minus epsilon. Right? You say, okay, well, right, we know that this actually makes complete sense, right? We know that T is of norm T, right? T is of norm T, right? And so we know that there's going to be an F1 of norm 1. There's going to be an F1 of norm 1 such that the norm of T of F1 is bigger than the norm of T minus epsilon, right? Okay. So that basically ends it for us, right? We know there's an F of norm 1 such that this is true. Right? And then we say, okay, so what we're looking for is a linear functional that that will take in this thing and just give us back the norm of it, But we can create that using the Hahn-Banach, using the corollary to the Hahn-Banach theorem. Okay. So I think it's best to read proofs backwards. That's the general rule. Think of what you're looking for. This is sort of like the forward way. It's like not as clear, I think, as thinking backwards. You say, okay, what are we trying to do? We're trying to show that this is bigger than that. That's the same thing as showing that this is bigger than that. Well, what do we have? We have that T is a bounded linear transformation, and we know that we can create a linear functional that just grabs that norm. That when given this, returns the norm. The end. Okay. So that is a nice application of Hahn-Banach. There's another, there are two more applications of Hahn-Banach in the chapter. One is this observation that L1 is not all of the dual of L infinity. L1 is not all the dual of L infinity. That is, you can create, I can use Hahn-Banach to show there exists some element of L infinity dual that cannot arise as L sub g. You remember we called these guys L sub g before you integrated against g. Okay. It turns out that you can create an element of the dual space that can't arise in this way. And then the second thing that is mentioned in this text is this business of creating a finitely additive measure that agrees with Lebesgue measure. I don't want to do that one. So if you want to read that, go ahead. That's a nice application of Hahn-Banach, but I don't think it's a crucial one. So let's skip it and let's go on to chapter 2. So please read this one by yourself. It's not that hard to read. And then next time let's go on to chapter 2. Okay.